Good evening, welcome to my laboratory. What you're looking at there is the MHOP, the MileHigh Op-Amp pulse motor driver, driving its rotor. And what I want to do now is demonstrate some waveforms. So this is my laboratory, and we have the Tech 2213A displaying the Drain and Sense Coil waveforms from the MHOP pulse motor system. The top trace is the drain trace of the MOSFET, and the bottom trace is the sense coil output. The top trace is at 50 volts per division, and it's showing the battery voltage of 24 volts and then the 0 volt baseline when the MOSFET is on. This is a MOSFET switching a high side load, so when the signal is high here at battery voltage, the MOSFET is off. The MOSFET is on when the signal reads 0 or near 0 voltage. The bottom trace, it's DC coupled, and that's the 0 baseline. The bottom trace is the signal from the sense coil, and it is AC coupled at where are we? Is it 1 volt per division, and the baseline is actually 6 volts. So this is fluctuating around 6 volts by plus or minus about 1 volt or a little more. Okay, so you can see where the set points are for the comparator, there and there. So see how this is a nice squared off pulse at the top. That's because I have the diode switched in. The oscilloscope is a very handy way to tell your RPM changes because you can see it instantly on the frequency. What I'm going to do here is drag the rotor down a little bit by touching the edge of it, and you can see immediately that the rotor is slowing down because the frequency is increasing or decreasing. Now when I take the drag off, the frequency increases. You get more and more cycles per screen, so that means that the rotor is accelerating. And as you can tell, that was a very, very sensitive test of the RPM. So if I make a little change in the timing, say, I can see that went in the wrong direction. There, I'm changing it back. Now I went too far that way. So right in here, where the RPM increases to the maximum and doesn't decrease, that's where I know that I have the timing set properly. You see the previous video for an explanation of the way to set the timing. Okay, now I'm going to switch the diode out of the circuit. And you can see that there's acceleration going on. So we'll just let it climb back to a speed there. The wobbling you see is an artifact of the scope, my scope's trigger. If I tweak the knob a little bit, I can make that go away. But I want to let it accelerate a bit first. Let me see if I can make it go away by tweaking the knob a little bit. Yeah, okay. So now we're still accelerating. The scope is still jiggly. Okay. So it's just about reached a stable speed now. So I'm going to change the time base. Oh, we have been looking at 2 milliseconds per horizontal division. So I'm going to change that now to 1 millisecond per horizontal division, and I'm going to put one of those cycles right on the screen here, like that. Okay. So this spike here actually goes up to 400 volts or more up there. I'm cranking the position of that trace down, obviously, to try to show where the spike goes. And you can see how high it goes up there. But mostly what I want to show right now is this pretty ring down here. This represents the neon on, when the neon flashes, and then this is the remainder of the ring down. Now as I change the duty cycle, that is the set point control, I'm going to a longer and longer on duty cycle here. Now you can see the frequency is actually starting to decrease, so it's slowing down. Ignore the scope glitches. And then I can actually, well, let's see if I can get that, there we go, glitch free. So I can actually get right into the spike and turn it completely on. Focus, damn it. Which of course makes the thing slow down because it's not pulsing. So I do need some duty cycle in there. Focus. Sorry about that. Let me switch to manual focus here. Okay, sorry about that. Now we're in manual focus, and what you can see is as I change the duty cycle pot to to shorter and shorter on times, we get a longer and longer off time, and that ring is allowed to develop. But that also causes the frequency to decrease, which means the rotor is slowing down. So if I crank the set point control back to right about there, giving us a little bit longer on time, that allows the rotor to speed up to its fastest speed. So we have the diode switched across the load, we have the neon only across the load, we have the acceleration and deceleration of the rotor shown as the frequency on the scope, and we have the nice beautiful inductive ring down of that big drive coil, and here we have the ability to turn the drive coil all the way off and all the way on. So we have full control over the duty cycle and the timing, and we can instantly see whether our changes in any of those parameters are causing something to happen by looking at the frequency on the scope, whether the trace is moving to the right or the left. All right, thank you for watching.